Hello all, my name is Nicolas Ypsilantis and I will present our work on universal image embeddings, which is the outcome of a collaboration of people from Czech Technical University in Prague and Google. We focus on the task of fine-grained and instance-level image retrieval. Given an index set of images and a query image, the goal is to produce a ranked list of the index images, such that images of the same class as the query are ranked first. In our work, the term class can refer to either a specific instance, for example the Eiffel Tower, or a fine-grained category, for example a car model. Retrieval is cast as a nearest neighbor search problem, where index images and the query image are represented by an embedding vector. Deep networks are the common choice to produce these embeddings, and developing training methods for learning embeddings has been the main focus for the past years. Previous work has been focusing on learning embeddings that are domain-specific. That means that one has to train a different embedding network to retrieve cars, a different for landmarks, etc. These models are referred to as specialists in our work. When one wants to build a visual search system that can identify objects from many visual domains, the current setup is both impractical and expensive, as a large number of models would need to be developed and maintained. We propose a generalization of the current setup, which aims at retrieving objects from multiple visual domains. The task now has to be addressed by an embedding that is discriminative across all domains at the same time. Such a universal embedding is a challenging goal, as different domains provide different visual cues that are essential for fine-grained and instance-level recognition. We propose the first large-scale dataset for research in universal image embeddings, which we create by carefully combining 8 existing datasets from popular visual domains with real-world applications. It is an order of magnitude larger than existing multi-domain datasets. We define a standardized training, validation, and test split. For the latter two, we further split them into query and index sets in order to support retrieval evaluation. We require the use of 64-dimensional embeddings, a practical size for large-scale applications, and the retrieval is performed based on the Euclidean distance. Query images are compared against the index consisting of images from all the domains. For evaluation, we settle for simple and practical metrics, namely recall at 1 and mean precision at 5. We perform a set of evaluations of baseline approaches. At first, we evaluate high-dimensional off-the-shelf embeddings from popular pre-training methods. We see that Dino V2 pre-training is the best, followed by CLIP and then ImageNet. Then we fine-tune models on the proposed training split. We use a classification-based objective on top of the learned representation. We test 2 different setups for the classifier, which is only used in the training phase and then discarded. First, one classifier across all different classes of the merged training set. Secondly, a different classifier for each domain. Additionally, we test 3 different sampling schemes for forming the training batches, which always contain samples from one domain. First, in dataset size sampling, the next batch comes from a domain with probability equal to its proportion in the training set. Secondly, sampling follows a round-robin routine, which results in a balanced sampling across domains. Finally, we sample each domain according to the number of steps that a model trained on that domain only needs to achieve maximum performance. We observe that our fine-tuned 64-dimensional embeddings outperform the high-dimensional off-the-shelf embeddings by a large margin. Balancing the number of samples across domains is better than sampling according to dataset size, while sampling according to the number of steps that the specialized model needs works the best overall. A separate classifier per domain seems to work slightly better than the joint classifier on average. Furthermore, we train an assembly of 8 specialist models, one for each domain separately. We compare the performance of a query domain-informed model that uses this assembly, called the Oracle Plus Specialist model, with our best-trained universal model. We see that our universal model is on par in most domains, even winning in 3, using 8 times less parameters, and does not require the domain of the query image to be known at test time. Complementary to the proposed benchmark, we conducted the Universal Image Embedding Challenge in Kaggle. A different industrial dataset annotated for the purposes of the challenge was used, containing only the test split, while selecting the training data was left as a part of the challenge. The challenge attracted more than 21,000 submissions from over 1,000 teams. The solutions of the top winning teams shared some common design choices, whose effectiveness was also partially validated in our experiments. Large backbones with the clip initialization was shown to work the best, further fine-tuned with classification-based losses. Additionally, the training data selection was crucial, with the most popular datasets of choice also being part of the proposed unit dataset. Thank you.